Moving on, I'm giving you the greatest Taboada hits. He actually teaches a one-semester course on this. We condensed it in 3 PowerPoints, which are on the course homepage, and the details are there. Everything we have discussed so far is always illustrated just by one variable. Everything I've done so far. In real life, you can do much better than that in any good experiment. For example, it used to be that in turbulence measurements, one had a wind tunnel. It's a thing where you put models of the German warplanes in Göttingen, and you discover, you design better wings for the fighter pilots to do their stuff. But to measure effect of turbulence, what they used to do is they would put a hot wire in the tunnel. So the tunnel is 6 meters tall. There is a wire. There's a huge fan at one end, creating more noise than even in Howie from our air conditioning. That produces turbulence. And then you measure the resistivity of that wire because it's hot, and depending on turbulence, it gets cooled when it's a thin wire. And then you get one measure of turbulence, and you are very happy. You publish statistics of this one measurement, and everything you get out of this is wrong, but it's engineering, it's beautiful, it's wonderful. Now today, when we measure turbulence, we actually measure thousands of points moving in a fluid by particle velocimetry. And we have, thousands of measurements. So we have a huge vector of measurements, and they're very correlated, meaning that the nearby particles in a fluid are moving in a very similar manner for a short period of time, because the fluid, moves globally. It has lots of correlations. And same is true of neuroscience, as you saw in Professor Solja's lecture. And, all these subjects which are now modern in third millennium, which are all called, big data subject, they have this very similar structure that you have lots of measurements, but you have to figure out, what's correlated out of them. If you South Pole latest on ice cube, then you have a bunch of neutrino arrive. Find out where it came from, how much energy it had. So let's say then what you're measuring so-called joint probability distributions. So you have 2 variables, x and y. They could be, you have 2 variables, and you plot how they arrive. And now, because of 2 variables, you have to plot them in a plane. And probabilistic frequentist approach is that you have to box your 2-dimensional space. So instead of having boxes which are integral, now you have 2-dimensional boxes, and you compute probability that out of hundreds of thousand events, some of them end up in this little box. That little box is approximated by dx dy, and in continuum limit, this becomes a density distribution, which is a joint density distribution. Now, the main thing about these density distributions, and it's amazing how often people don't understand this, that it could be very useless even to squash them to be one-dimensional density distributions. You could be tempted as a graduate student to do your thing on a sub-dimensional subspace. So you're in 100 dimensions, but you decide to do your SVD or PCA or one of these fancy distributions on 3 dimensions out of 100, and you get something. And it's very hard to tell people to deprogram them when you have 70 dimensions. You have to do your PCA in 70 dimensions, not in projections. But here you don't appreciate it yet. And what's the problem with frequentist approach in higher dimensions? The more dimensions you have, you need to be in a small cube. So if you have a cube that's of length, 0.1, its volume in 3 dimensions will be 10 to the minus 3. So in very high dimensions, likelihood it ended up in small cube goes like your epsilon size of your cube to the power of dimension. That can be a very small number. It can be very hard to produce these probability distributions in higher experiments. But in this textbook example, we don't worry about it. From it, you can extract these things, which are called, I do not know why, marginal probability density distributions, in which you decide that, yes, there are 3 variables, but I can't resolve one of them well enough, so let me just integrate over it. So you can find probabilities of this thing projected down just on the x-axis or on the y-axis. Those are called marginal PDFs. And you would like to have some test whether the things that you're measuring are actually independent measurements of your experiment, or you're measuring same thing twice. So for example, if you're measuring velocity of 2 particles in a fluid which are very close to each other, even though you have millions of dimensions, you get almost no information from the second one because they're totally correlated. But if they're very far apart, then you're measuring something where you can assume independence. For that, you define conditional probabilities in which you measure function of y and you treat the other thing as a parameter. So what it means is you take little boxes here and you measure probabilities at different times, and you would like to know where they're uncorrelated. And if they are independent, then you'll find out that this conditional measurement of y given x and g given y, the other way, they're independent of the other parameter. That's what you mean by independent. But in this particular case, they're not, because it's the same distribution which you've sliced in some way. That's not a good way. For that reason, you do what we have done so many times already. You define a covariance and you decide that the way you have to measure this, you have to think of these distributions as ellipsoid cigars in higher dimensions. And you have to find out, what's expectation value of x and y as 2 variables. If it's a discrete distribution, this is a matrix, but if x and y are continuous, this is a function of these 2 indices, but a symmetric variable, which you obtain by taking your probability distribution PDF for the two functions and measuring their product and subtracting the means in the usual way. This gives you new variables. And the point of now of understanding what our singular vectors are is that there is a way of turning over this Gaussian in such a way that in new coordinates given by eigenvectors of this matrix, whose length is the standard deviation measured along that, we actually decorrelate them. So in new variables, they're orthogonal, and each one of the directions is not correlated to the other ones. So, that's another way of understanding what going to the intrinsic coordinates of the problem means when you have a probabilistic measurement. So the main thing is when you go from cigar sitting someplace in the state space, you move the mean to the origin, then you rotate the origin by SVD or PCA in such a way that the new axis is orthogonal axis. You have gotten a representation where your probability, if it's normal probability, has gotten decorrelated. So then what people do, and it's slightly iffy in my opinion, but that's what they do, is they define a unitless correlation coefficient by taking this matrix and dividing it by standard deviations along X and Y. This you can do from experimental measurements. And this gives you a correlation coefficient matrix, because if I look at diagonals when X equals Y, then, this is sigma square divided by sigma square. So that's on diagonal, I get ones. But off diagonal, I get this dimensionless measure of correlation. And if things are uncorrelated, you would like this to be zeros. And that's a measure of correlation coefficient, which I've given you a problem to work out.